Chapter 7F, Vibrations and Rotations, including molecular spectroscopy. Using particle-in-a-box model, we have studied how electrons move inside the molecules. The solution to the Schrödinger equation leads to the molecular orbitals of the pi electrons. The molecular orbitals describe the translational motion of the electrons. In this section, we are going to study the interaction between atoms inside the molecule through chemical bonds. These are vibrational motion of diatomic molecule and the rotational motion of diatomic molecule. Before we study vibration of diatomic molecule, let's go over classical mechanics of vibration, the harmonic oscillator. So here we show a mass attached to a spring, and x naught is the equilibrium position. So a spring with a mass at equilibrium position. If we pull away from its equilibrium position, for example, to the right side, the spring will resist the change and exert a force to the left side. So the force displacement are in opposite direction. If we compress it to the left side, the spring will exert a force to the right side. And so this is described by the Hooke's law. Force F equals negative kx. Negative indicates the force and displacement are in opposite direction. K is called force constant, which measures the stiffness of the spring. So if we pull away from equilibrium position and let it go freely, then it will vibrate back and forth, which we call a harmonic oscillator. According to Newton's law, force equals ma, and a is the second derivative of the displacement over time. So now we have a second order linear differential equation. Same equation we introduced when we solve Schrödinger equation in 1D box model. So combined with the characteristic equation and the boundary condition, we can solve this, and the solution is a sine function of time. So displacement sine square root k over m times time. So if we plot it, this is shows how the displacement change with time. This square root k over m is called angular frequency, which measures how many radian per second. Divided by 2 pi. This will give you the natural frequency, which measures every second how many vibrations the spring undergo. It is important to notice that the frequency is proportional to square root of k and inversely proportional to the square root of m. So the more stiff the spring or the stronger the bonds, the faster it vibrates. And the lighter, the smaller the mass, or the lighter the atom, and the higher the frequency. Also important to notice that this frequency has nothing to do with energy. So if the system obeys Hooke's law, the energy should equals to half kx squared. Okay, this equation to calculate the potential energy of the vibrator. So you see, if x is 0, if you don't pull it, the energy can be 0. And the larger the x, the larger the energy. And therefore, in classic harmonic oscillator, the oscillation has a constant frequency determined by force constant and the mass. The energy can be any value, and energy frequency are not related. Let's look at the energy of classic harmonic oscillator, which is half kx squared, and the plot is a hyperbola. The equilibrium position is here. So if the object is pulled away, let's say x1 from its equilibrium position, then the energy E1 is half k x1 squared. If the displacement is x2, then the energy here is half E2 is half k x2 squared. So again, you can see the energy can be any value, can be 0, can be E1, can be E2, or can be any value here. If the displacement is x, the energy is half k x squared. We just showed how classical mechanics describe a harmonic oscillator where you have one object attached to a spring. This is called a one-body system. When we think about a diatomic molecule, you have two atoms, okay, connected by a bond which is equivalent to a spring. And this is called a two-body system. So how in classical physics describe a two-body system? It turns out that the two-body system can be reduced to one-body system if we calculate the mass using this equation. M1 times N2 divided by M1 plus N2. This is called a reduced mass. If we do that, then the two system becomes equivalent. And therefore, the frequency of this system can be calculated by 1 divided by 2 pi square root of k over mu. Here, mu is the reduced mass. In summary, if a diatomic molecule can be considered as a harmonic oscillator of a two-body system, in classical mechanics, it has a natural frequency 1 over 2 pi square root of k over mu. So this frequency is determined by the force constant, which measures the bond strength, and the mass. Here is the reduced mass of two atoms. The energy can be any value, which is described by half k x squared. So the energy of the harmonic oscillator and the natural frequency are not related. And this is a conclusion from classical physics. Having looked at the classical mechanics of harmonic oscillator, now we turn to quantum mechanics, because we know at a molecular level quantum mechanics has to be used. So here is the Schrödinger equation, where we have kinetic energy operator, which is second derivative. Now note that this is reduced mass of the two-body system. Here is the potential energy of the harmonic oscillator and total energy E. Now remember, in 1D box model, potential energy is 0. So that makes the equation second order linear differential equation, which can be easily solved. But in this case, potential energy is a function of x, and that makes this equation non-linear. And although we can solve it, it takes too much time for the class. So here we are going to show you the result. So just like we did in 1D box model, when we solve Schrödinger equation, we combine with boundary condition, and that leads to the energy and the wave function, only certain of them are allowed, and that means they are quantized. Okay, we're going to show you the energy and allowed energy and the wave functions in the next few slides. Here we show the first 4 allowed energies and the wave function associated with these 4 energies. When solving Schrödinger equation, the solution to the wave function is called eigenfunctions. and the energies are called eigenvalues. The equation of these energies is Planck constant times nu. Okay, nu is 1 over 2 pi square root k over mu. Now, if you remember from the previous slides, and this is the natural frequency of the vibrator come from classical mechanics. So it's interesting to see that when we solve Schrödinger equation, the allowed energy is proportional to the natural frequency that comes from classical mechanics. Now, V is a quantum number. Allowed values are 0, 1, 2, 3, 4. Just like when we solve 1D box model, you have a quantum number. Here, we have a quantum number that we use symbol V, but some textbook with N. It doesn't matter which one you use. You have a quantum number, all right? Energy is determined by a quantum number that has allowed values 0, 1, 2, 3, 4, 5. Another way to write this energy is use h bar times angular frequency, and then a quantum number plus 1.5. So the allowed energy in quantum mechanics are proportional to the natural frequency derived from classical mechanics. Another thing that is interesting is in this diagram that in classical mechanics, the energy is half kx squared, depicted by this green curve. And you can see the energy can be any value, can be 0, all right, or can be any other values. However, in quantum mechanics, the allowed energy can only be here, lowest energy, and then the one above it, and then another one, the third one, and then the fourth one. So these and go up. So you only have certain allowed energies, and the lowest energy here is not 0. All right, and that's very different from classic mechanics. This is called 0-point energy, which says the particle has the lowest and non-zero energy. Having looked at the first few wave functions, now let's look at the probability distribution by squaring of these wave functions. And we can see the lowest energy one, the most probable place, is at the center. But when we increase the quantum number from 0 to 5 to 10, the most probable place shifts towards the two ends. And the wave function in the middle becomes smaller. So when you increase the quantum number extremely high, you would expect the highest probability is at the ends, and the probability in between becomes negligible. So let's think about the classic mechanics of vibration. So if this is equilibrium position, the particle will move fastest here because it has highest kinetic energy. And then the kinetic energy is converted to potential energy, so the particle moves slow, 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 and until the right ends, it stops here and move back. And then become faster, faster, and faster here, and then become slow, slow, and then stop at the left side. And then the potential energy change to kinetic energy, go faster, and then become slow at two ends. In other words, classic particle slowest at the two ends. It spends most of the time at the two ends, and that's called turning point. So here, as the quantum number increase, the position of the highest probability migrate towards the classic turning point. And that is another example of corresponding principle. Another thing to notice that for classical mechanics, And the energy is described by this blue curve. So if you have energy this high, then the particle will vibrate between these two turning points. So this point, 2 points are the turning point. But in quantum mechanics, at this energy level, the wave function actually pass past this turning point to here. The harmonic oscillator can tunnel into classic forbidden displacement. Let's look at the diatomic molecule vibrational energy levels and how they interact with light. And this shows the first few allowed energy levels. And the equation of the energies are Planck constant, nu times v plus half. Nu is called the natural frequency of the vibrator, and nu is the quantum number. So the quantum number here can be 0, 1, 2. All right. Now, if you shine light to the molecule, if the energy of the light photon matches the energy difference between two energy levels of the molecule, then the molecule may absorb the photon and excite from the low energy to the high energy. So in this equation, delta E is the energy difference between two energy levels of the molecule, and on the right side is the energy of one photon. Now the photon energy is Planck constant times frequency nu of the photon, and OBS means absorption. So if that happens, the molecule will absorb this photon energy. Okay, so you see you have two nu, one v nu absorption, that's the photon frequency that will be absorbed, and the other is the natural frequency here, which is used to calculate the energy difference between the two energy levels of the molecule. So how these two frequencies are related? Okay, we're going to derive equation in the next slides. In the last slides, we mentioned that when incoming light, the energy of one photon equals the energy difference between two energy levels of the molecular energy, then the molecule will may absorb that photon and excite from low energy level to the higher energy level. But that's not the only the requirement. And in quantum mechanics, there are selection rules. For vibration, the selection rule says delta V has to be positive, negative 1. So the lowest energy level V is 0, and then 1, 2, and 3. So from 0 to 2, that is not allowed because delta V here is 2 minus 0, that's 2, which disobey this selection rule. So from 0 to 1, that is allowed because delta V is 1. From 1 to 2, okay, delta V is 1. From 2 to 3, delta V is 1. In other words, the absorption can happen only between adjacent energy levels. Now let's calculate this energy difference. And the lowest energy is V equals 0. So when this is 0, the lowest energy will be h nu divided by 2. So when V equals 1, so 1 plus half is 3 over 2. So this will be 3 over 2 h nu. And then 5 over 2 h nu, 7 over 2 h nu. So what's the difference, delta E, between the first and the second energy level? Is 3 over 2 minus 1 over 2, and that's 1. So this is h nu, just h nu. And what about 2 to 3? 5 over 2 minus 2, 3 over 2, that's again h nu. And between 2 and 3, is again h nu. So the energy difference between adjacent energy levels are all the same, is h nu, h nu, h nu. Nu is the natural frequency of the vibrator. So in order to absorb light, this energy difference has to equal to the energy of the photon. The photon energy is h times v nu of the absorption photon frequency. So when this equals the energy difference, which is h times natural frequency, we find that the absorption frequency of light equals the frequency of the natural of the vibrator. So it is interesting to see that first we say the energy has to match, but now for the energy to match, the frequency has to match. Okay, so when the frequency of incoming light, all right, match that of oscillator, okay, in other words, when the photon has a frequency equal to the natural frequency of the vibrator, then it will absorb the light, the molecule will absorb the light and jump to a higher energy level. In addition, the energy difference are all the same, and therefore they absorb the same frequency. So they all absorb the frequency equal to the natural frequency, and therefore only one frequency is absorbed in this vibration under harmonic oscillator model. And the frequency falls in the infrared range. And we'll see this in the examples in the future. Example, the force constant of bond in diatomic molecule hydrogen chloride is 516.3 Newton per meter. Calculate the 0-point energy of this molecular oscillator and the separation of adjacent energy levels. So hydrogen chloride is a diatomic molecule. All right, we can think about it as two atoms connected by a spring. So this is M1, this is M2, and the two-body system can be reduced by one-body system with a reduced mass. And the reduced mass is calculated by M1, N2 divided by M1 plus N2. Okay, and in this equation, these are the mass of individual atom. Now we know the molar mass, so we can use molar mass, but you need to divide by Avogadro's number. So you can use a conversion factor. Okay, whenever you use molar mass, you need to times this conversion factor to calculate in each atom or molecule. Now you can also divide by Avogadro's number. So divide by Avogadro's number, but also remember the mass here is gram per mole. So the SI unit is kilogram, and therefore you need to divide by 1000. Okay, so when you do that, you will get this this number, conversion factor, 1.67 times 10 to the negative 27. Now Avogadro's number is 6.02 times 10 to the 23rd. So you can try that. You should get this value. And so the reduced mass for hydrogen chloride is 1.64 times 10 to the minus 27 kilogram. All right. So the natural frequency of vibrator from classic physics is 1 divided by 2 pi square root k over mu. Mu is the reduced mass. K is the spring constant. So plug in. All right. So you get natural frequency to be 8.94 times 10 to the 13 hertz. Okay, this is natural frequency. So these are all come from classical physics. When we solve Schrödinger equation, the energy is quantized. The energy should be h nu. Nu is just this natural frequency times a quantum number v plus half. So what is the lowest energy level? Called the 0-point energy. That's the non-zero lowest energy level when V is 0. So that gives you half h nu, and the answer is 2.96 times 10 to the minus 20 joule. So that's the 0 point energy. Okay, what's the separation of adjacent energy level? In the previous slides, we derived equation and showed that the adjacent energy level are all the same from 1 to 2, 2 to 3, 3 to 4. They are all the same, which is just h times nu. So here is 5.92 times 10 to the minus 20 joule. Now in the next slides, we show that this energy falls in infrared range. This shows the ranges of electromagnetic spectrum. So high energy end start from gamma ray and then X-ray. These are very high energy electromagnetic spectrum. And then UV, and then visible. So visible high energy end is blue and the low energy is red. And then goes to infrared, has lower energy than the visible range. And then goes to microwave, and the lowest energy is radio wave. We just showed that when molecules vibrate, the energy is quantized, and that energy falls in infrared range. So if you shine lights, the molecules vibrate and absorb light in the infrared range. Now in the last section, in the particle in a box section, we showed that electrons can also absorb light from one molecular orbital to another molecular orbital, and that falls in the UV range, so higher energy. So electronic transition has energy higher than the vibration of the bonds. And later we'll show you molecules also rotate. The rotation also give you quantized energy levels, and that energy falls in microwave. And so rotation has lower energy, vibration of the bonds has higher energy, and the electronic transition has highest energy. One thing I want to mention is the unit of the frequency. When we use this equation to calculate either the natural frequency or the absorption frequency of light for vibration, the unit is in hertz. But the spectroscopist prefer another unit called inverse centimeter. So how do you find inverse centimeter? All you need to do is divide by speed of light. Now speed of light, usually we say 3 times 10 to the 8th power meter per second. But here it should 3 times 10 to the 10th power centimeter per second. And when you divide by this value, the unit will be inverse centimeter. We already introduced the selection rule of vibrational absorption of infrared, and that is delta V equals positive negative 1. In other words, the absorption can only happen between adjacent energy levels. This is selection rule number 2. And there's another selection rule for vibrational absorption, and that is electronic dipole moment of molecule must change. So dipole moment must change. For example, hydrogen chloride, and hydrogen is partially positive and chlorine is partially negative. So this bond has a charge separation, and the dipole moment is calculated by this charge separation multiplied by the bond length. Okay, so the charge times bond length. So when the molecules vibrate, for example, it becomes longer, the bond length increase, and then the dipole moment change. And for hydrogen chloride, then it will absorb the infrared because dipole moment changes. Now what about the nitrogen gas? Nitrogen, two nitrogen atoms are the same. The molecule is symmetric. There's no charge separation. So when the molecules vibrate, there's no dipole moment change. So nitrogen gas will not absorb infrared. Okay. Similarly, hydrogen gas, all right, hydrogen, nitrogen, they don't absorb because there's no dipole moment change. Now, carbon dioxide is quite special. So, COC, all right. Now, this has 3 atoms, so they have different vibration mode. One vibration mode is when this bond go to the left side, and this goes to the right side, the other goes to the left side. And this will cancel the change, and therefore the dipole moment does not change, and this mode of vibration does not absorb light. However, it has another vibration mode where the bond both goes to the same direction, and this will change the dipole moment, and therefore this will absorb infrared. So CO2 may absorb infrared. Okay, one of the modes absorb, one of doesn't. Example: the infrared spectrum of boron fluoride consists of an intense line at 380 inverse centimeter. Calculate the force constant of boron fluoride. Boron fluoride is a diatomic molecule. Under harmonic oscillator model, the energy is quantized, and the allowed energy should equals to 1/2 pi, so 1/2 pi square root k over mu. So this is hertz, and this is inverse centimeter. So we should use this equation. Okay, now this frequency is 380, and we want to calculate the force constant, and therefore first we need to calculate the mu. Mu is the reduced mass. So we already see how to calculate the reduced mass, which is m1 m2 divided by m1 plus m2, and because 75, 8, 19 are molar mass, well, so we times conversion factor to calculate the mass of individual atom. All right, you can also divide by Avogadro's number and divide by 1000, as we show in the last example, and that give you 2.53 times 10 to the minus 26 kilogram per molecule. So plug in the equation, so K can be calculated, which is 129 Newton per meter. Under harmonic oscillator approximation, the vibration of chemical bonds leads to quantized energy levels, and the separation between adjacent energy levels are all the same. And therefore, this theory predicts that the absorption of light by vibration will give you only single frequency absorption, and that is the natural frequency of the vibrator. However, when we perform infrared absorption of the molecules, usually we see a broad absorption like this one. Sometimes there's a deep minimum at the center. And this can be explained after we introduce the rotation of the molecules, because when molecules vibrate, they also rotate, and the rotation also absorbs light. Infrared is a very useful tool for chemists to identify the chemical bonds. This table shows some diatomic molecules, their vibrational frequency, and the K constant. The stronger the bonds, such as nitrogen, which has a triple bond, CO triple bond, they have large K constant, and therefore they give you high vibrational frequency. Okay, according to the equation 1/2 pi square root K over mu. So the larger the K constant, such as triple bond, the higher the frequency. So in this infrared range, the triple bond, carbon-carbon triple bond, nitrogen triple bond is in the range of 2,100 to 2,300 inverse centimeter. For double bonds, all right, they will absorb infrared at about 1,500 to 1,800 because they're weaker than triple bond, and then the single bond is at below 1,460 inverse centimeter. Now, whenever you have a bond involves hydrogen, for example, nitrogen-hydrogen bond, oxygen-hydrogen bonds, carbon-hydrogen bonds, the reduced mass becomes very small because of the hydrogen. And so if you have a small reduced mass, the frequency is also high. And so therefore you see any bonds involves hydrogen, they will have vibration frequency above 2,800. And therefore, if you have an infrared that contains a bond, contains absorption at around 1,700, then you know that the molecule may have a carbon-oxygen double bond. And if you have a absorption at 2,300, then you may have a carbon-oxygen, a carbon-carbon double bond, a triple bond, or nitrogen carbon-nitrogen triple bond. In summary, under harmonic oscillator approximation, the vibration of chemical bonds leads to quantized energy levels, and the energy is calculated by Planck constant times nu times V plus half. Nu is the natural frequency of the vibrator, which is 1/2 pi square root K over mu. V is a quantum number, which can be 0, 1, 2, 3, 4. The energy are equally spaced between adjacent energy levels, and therefore there's only one absorption frequency that is predicted in infrared range. This is the absorption frequency of the light, and this is the natural frequency of the vibrator. Using this equation, the unit is in hertz, and when you divide by speed of light, the speed of light should write at 3 times 10 to the 10th power centimeter per second, then the unit will be inverse centimeter. Again, the absorption frequency of the vibration falls in infrared range. Using these two equations, you can calculate the force constant if we can measure the frequency of the light that can be absorbed. And the selection rule 1 is the delta V equals positive negative 1, and therefore the absorption can only happen at adjacent energy levels. And the second, the dipole moment of the molecule must change during the vibration. So far we discussed chemical bonds vibration under the harmonic oscillator approximation. The chemical bonds are thought of as springs that has force constant and obeys Hooke's law, and the potential energy is half kx squared, a parabola. Now you may have experienced that if you have a spring and if you pour too far away from its the equilibrium position, it may lose elasticity and won't come back. That's the same happens for chemical bonds. If the displacement is too far away from its equilibrium position, the chemical bond may break and the molecule may dissociate into atoms. So you see, here is the harmonic oscillator approximation, and this is the real chemical bonds vibration. So the harmonic oscillation is a good approximation near the equilibrium position here. It is a poor approximation at the higher energy level. Okay, deviate. Okay, and it is totally run near the dissociation limit. At higher excitation energies, the motion becomes anharmonic. Okay, so we call here anharmonic, and the distortion force is no longer proportional to the displacement. So in the next few slides, we are going to briefly discuss anharmonicy. Morse potential has been used to simulate the real potential energy of vibration. In this equation, dE represents the dissociation energy, x is the displacement, alpha is a combination of many constants. So when x approaches 0, this function becomes 0, and that's the bottom wall. When x approaches infinity, the function becomes hc times dE, and that's the dissociation energy. Apply Schrödinger equation with this Morse potential energy. The allowed energy can be solved, and this is the equation for the allowed energy levels in terms of wavelength. And in this equation, you have a quantum number v. And so v plus half, that's the first term, times nu. This first term is the same as we obtained from harmonic oscillator. Now the second term is due to the anharmonicity, and xe is called the anharmonicity constant. So that represents anharmonicity. So by using Morse potential, all right, we have a allowed energies that one comes from harmonic oscillator, another comes from anharmonicity. One important feature you can see here, the adjacent energy level separation are different, while in harmonic oscillator they are all the same, and therefore we predict only one absorption frequency. But here they become smaller. We'll see some results in the next slides. Under harmonic oscillation approximation, the allowed energy separation between adjacent energy levels are all the same. And a selection rule says that the delta V has to be positive, -1. That tells us the absorption can only happen between adjacent energy levels. And this is V equals 0, 1, 2, and 3. So the absorption between 0 and 2 is not allowed because delta V is 2. That against the selection rule. However, if the vibration has an anharmonicity, then this absorption is possible. And this is called the first overtone transition. 0 to 3 will be called second overtone. And in this diagram, we see here, this is the absorption between adjacent energy level from 0 to 1. And that's called fundamental. This is the only absorption allowed in harmonic oscillator. But if with enharmonic, we also see the first overtone, the second overtone, although the intensity is extremely low compared to the fundamental absorption. Now, according to this diagram, the first overtone is about twice energy of the fundamental absorption. So here, the wavelength for the fundamental is 2890, and the first overtone is 5682. It's about twice. That makes sense. Similarly, the second overtone is 8333, which is about 3 times the fundamental absorption. Morse potential is not the only one used to simulate the potential energy of the vibration. There are other functions that has been used. The solution to the Schrödinger equation is similar as the Morse function, and that is the allowed energies in terms of inverse centimeter includes first one is the harmonic oscillator, comes from harmonic oscillator, and then here is the enharmonic. You have an harmonic constant, and there are more terms includes enharmonic. They all relate to the dissociation energy. So using these equations, we can calculate the fundamental transition, the first overtone, the second overtone. So here V equals 0, V equals 1, V equals 2. So first overtone, the theoretical prediction is this equation, in which nu represents the natural frequency of the vibrator, and here second term include a enharmonicity constant. So that's the fundamental transition. The first overtone prediction is also includes natural frequency of the vibrator and the enharmonicity constant. Now, the fundamental transition frequency and the first overtone can be easily measured by infrared absorption spectroscopy. And then using these two equations, we can calculate the natural frequency of the vibrator and the enharmonicity constant Xe. I will show you in the next slides. Estimate the enharmonicity constant Xe for chlorine fluoride. The fundamental and the overtone absorption frequency in terms of wave numbers are found to be 773.8, 1535.3 inverse centimeter. Now, in the last slides, we already showed that allowed transition in terms of wavelength number is this equation, and in theory, we can predict the fundamental transition is this equation, which includes natural frequency and enharmonicity constant. That's the one we are going to solve. And this first, the fundamental transition is 773.8. Similarly, the first overtone is 2 times nu minus 6xe times nu, which is 1535. That is measured. So combine these two equations. Okay, we can solve nu, which is a natural frequency, and the enharmonicity constant. Here again shows the electromagnetic spectrum range, and so from high energy gamma ray, X-ray to UV to infrared, then to microwave to low energy radio wave. And we showed so far that the molecules vibrate, and the vibration has quantized energy levels, and that energy corresponds to infrared range. So next we are going to discuss rotation. When molecules rotate, the energy is also quantized, and that energy will fall into microwave range.